Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, I'll be covering how to calculate heat and what happens when heat is transferred. Let's get started. As we mentioned in previous videos, remember that heat is an example of thermal energy that can be exchanged between the system and the surroundings. Remember, heat is going to happen whenever heat exchange is going to happen when there's some difference in temperature between the two. Heat is an example of a kinetic energy, which means it's constantly in motion. And so the temperature is the measure of the amount of thermal energy within a sample of the matter. So important for us to remember that heat is going to flow from matter with high temperatures to matter with lower temperatures until they both reach some type of equilibrium between those two temperatures. Now, the amount of heat that an object can absorb is based on this theory known, or this idea known as heat capacity. So the capacity, how much are you capable of holding? So when a system absorbs heat, as heat comes into the system, we expect that the temperature is going to increase. Well, how much that temperature increases is going to be based on what the heat capacity of the material is. And so there's a constant that we use that is known as the heat capacity constant, or capital C, that can be used to predict the overall heat that an object now has as it gains or loses these temperature changes. And so the heat capacity has units of joules per Celsius or joules per Kelvin, and can be implemented to actually calculate the overall heat of an object. And we can multiply that by the change in temperature. Again, that delta symbol, that triangle symbol meaning change. Now, the larger the heat capacity of an object that has, the smaller the temperature change will be as we add in some amount of heat. So that means that, if I have a really, really high heat capacity, that means before you start seeing my temperature change, I'm going to be able to absorb a lot of heat before that starts happening. And vice versa, if I have a small heat capacity, then I'll have a really sharp increase in temperature as more heat is being absorbed or lost. So there are a number of factors that can affect the heat capacity. First, the heat capacity of an object depends on the amount of material that's present, or the amount of matter. And so normally when we're measuring matter, we're going to measure its mass. What's the mass that's present? And so if we have 200 grams of water versus 100 grams of water, 200 grams is going to require twice as much heat to raise it by 1 degree Celsius compared to 100 grams. Then also the thing we have to remember that's going to determine or affect the heat capacity is the type of material that we're dealing with. If we think about like the sand when we go to the beach, the sand at the beach, it's very, very hot when we're walking there. You're probably tiptoeing around there. However, the water that's at the beach is normally much cooler. They're both being exposed to the same sun rays. So why is that? Well, the heat capacity of the sand is much lower than that of the water. So as the heat is being absorbed by the sand, the temperature shoots up, whereas the water is able to absorb more and more heat before we start seeing those temperature changes. And so again, the higher the heat capacity, the slower that temperature change will be. So different materials have different heat capacities associated with them, and this is considered to be an intrinsic capability. And so we can actually define what's called the specific heat capacity, which tells us the amount of heat that's required to raise the temperature from 1 gram of one substance by 1 degree. So you'll look, the unit looks very similar to just heat capacity by itself, but there's a subscript of the S on the bottom that is also present. And so this now is incorporating the mass unit. So the units for heat capacity, specific heat capacity, are joules per gram per Celsius or joules per gram per Kelvin. And you can see that there's a large range of materials that are found with a variety of heat capacities. But this information is what's the reason why when you're cooking in different types of pans, they give you different temperature suggestions on the back of the box, like if you're making brownies or cookies, because the materials, whether you're using like a Pyrex pan or an aluminum pan, will all absorb the heat from the oven differently. And so you have to adjust your temperature settings and the amount of time you're cooking accordingly. Important to note, you'll see that water has a very, very high heat capacity, which is part of the reason that we use it in things like our automobiles to help keep our systems cool, because it can absorb a lot of heat without reflecting a huge degree in change. It's also important to note out that the specific heat are considered to be intensive properties. So we learned that word back in chapter 1. An intensive property is a property that can be used for identification. So again, as we mentioned earlier, the specific heat of water is extraordinarily high. It can absorb a ton of heat before you start seeing a large change in the temperature. And so it's the large amount of water that's in the air that's also around beaches that helps it keep cool. And it's also the reason that we're able to survive on Earth. Without water, the temperature would be on average 170 degrees Celsius. And so the water is a natural coolant for the environment. It's also used as a coolant whenever we think about, like I said, our automobiles, because it's able to help prevent mechanical parts from overheating. So when we want to quantify the amount of heat that's in an object, we can actually calculate that if we have some knowledge about certain parameters. If we know the mass of the object or the type of object it is and subsequently the specific heat or the temperature change, we can use all that information to solve for our heat amount. So the heat can be calculated through a very simple equation, which is that Q is equal to the mass times specific heat times your change in temperature. Again, thinking about units, your mass is grams, specific heat is joules per gram per Celsius or Kelvin, and your change in temperature is going to be degrees Celsius or Kelvin, depending on the situation. It's important to note that whether you're dealing with a temperature in Kelvin or Celsius, the change in temperature, whether it's Kelvin or Celsius, would be equivalent to one another, because you don't actually add the 273 to the change, you add it to the final and initial values. And so because you're adding it to the final and initial values, not the change itself, the magnitude of the change is equivalent, whether you're in Celsius or Kelvin. Just remember that. So we can go ahead and put all this to work. So it says how much heat is absorbed by a copper penny with a mass of 3.1 grams, whose temperature rises from -8 to 37 degrees Celsius. And so here we're looking for the heat of the object. And we know that the formula is going to be the mass times specific heat times delta T. And so we would have to look on that chart and look up what the specific heat of our copper is. And we see that the copper specific heat is equal to 0.385 joules per gram per Celsius. We can then plug all the rest of the information into this simple calculation. So the mass, which we see is 3.1 grams, times the specific heat, 0.385 joules per gram per Celsius. And the change in temperature, you can put it in as, well, my final, which is 37, minus the initial, minus 8. So we get positive here, okay? And so we plug all that into our calculators. So I'm going to do that change part first. So 37 plus 8 gives me 45 times 0.385 for the specific heat times 3.1 for the mass. When I do so, I end up getting a heat value of 53.7, and the units would end up being, well, grams cancel, Celsius cancel, and so what we're left with is joules. Notice that we get a positive value out, and that makes sense because of this word here. It's telling us that we're absorbing the heat. Heat is coming into this copper penny, and so we can use that to help kind of verify our answers. Okay, so check your answers, and then we will move on. Great. Okay, so the next problem says calculate the amount of heat released, think about what we should be expecting there, when 7.4 grams of water cools from 49 degrees Celsius to 29 degrees Celsius. And so again, here we're looking at the heat that's being released in this case. So that word release, you should be triggered to say, okay, this likely means I should come up with a negative value because it's losing this heat. It's releasing this heat out to the surroundings. So we can then plug in our mass, which is 7.40 grams, times the specific heat of 4.18 joules per gram per Celsius, times delta T, which would be 29 minus 49 degrees Celsius, or negative 20, excuse me. And so we plug that in. We have negative 20 times 4.18 times 7.4, and that will give us negative 618.64, or with proper sig figs, negative 6.2 times 10 to the second. And again, our units are going to come out as expected energy units of joules. Okay, check your answers. Good job. All right. And so we can also use this information to help us to figure out how much heat is being transferred between hot and cold objects. Remember, when we place two objects that are at different temperatures in contact with one another, the heat from the hot object is going to leave it and go into the cold object, and the cold object is going to continuously be raising its temperature. Now, that heat flow process is going to continue until the two reach some thermal equilibrium. Now, the amount of energy that's lost by the hot material is equal but opposite to the amount of energy that's gained by the cold material. And so we can come up with this idea that the heat of the object, of the hot object, is equal to but negative to the heat of the cold object. So that means that the hot object technically lost that amount of heat and the cold object has gained that amount of heat. Well, we can expand that idea out even further by plugging in the heat equation that we've seen previously, where we now take into consideration the amount of each of those materials that's present, the specific heat of each of those, and the change in temperature. Remember, for both of these, regardless of which side of the equation you're dealing with, the T final, your final temperature, is going to be the same on both sides, because that's the thermal equilibrium that you're obtaining. Now, the initial may not be the same, and it shouldn't be the same because one's hot, one's cold. But again, when we put all this together, the amount of heat lost by the hot object is equal to, but opposite, the amount of heat gained by the cold object. And so here it says a piece of metal is added to water at 25 degrees Celsius. The final temperature of both the metal and water is 30 degrees. Which of the following is true? And so we have a couple of options. Heat lost by the metal is greater than heat gained by the water. Heat gained by the water is greater than the heat lost by the water. Heat lost by the metal is greater than heat lost by the water. Heat lost by the metal is equal to the heat gained, or we need more information. Well, we know that number 4 would be the correct answer, because the hot object loses is equal to but opposite what the cold object gains. Okay. All right, so let's try putting this into a problem. It says a 35 gram cube of aluminum initially at 45.8 degrees Celsius is submerged into 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both substances at thermal equilibrium? Okay, so we're looking for the final temperature. Now, some information that we know that the mass of the object is equal to 32.5 grams of the hot object. The initial temperature of aluminum is 45.8 degrees Celsius. The mass of water is 105.3 grams, and the initial temperature of water is 15.4. We are ultimately trying to find this final temperature, okay? And so this is where we're going to want to exploit this idea that Q hot, the hot object, what it loses is equal to what the cold object gains. And then we're going to expand this idea out to say, well, this would be equal to the mass of the hot object times the specific heat of the hot object times the change in temperature for the hot. And that's equal to, but opposite, the mass of the cold object times the specific heat of the cold object times the change in temperature of the cold object. So then we're ready to plug in. The mass of the hot object, remember the aluminum is the hot thing, so we would say 32.5 grams times the specific heat of aluminum. And so we would have to refer back to that chart that we had previously. So the specific heat of aluminum is 0.903 joules per gram per Celsius. And then the delta T of the hot object, well, we don't know what the final temperature is, but we do know that we started at 45.8 degrees Celsius. And so then we would set that equal to, but opposite, the cold object side. So the cold object, we had 105.3 grams times the specific heat of water, which is 4.18 joules per gram per Celsius. And then we're going to multiply that times the final temperature minus the initial, which in this case is 15.4. Okay. It then becomes an algebra problem. So we're first going to take 32.5 times 0.903, and that's going to get us 29.3475 times TF minus 45.8, and that's equal to, but opposite. Now we're going to do the parentheses on the other side, 105.3 times 4.18, and that gets us 440.154, still multiplying times TF minus 15.4. And then we distribute those values through. So this would become 29.3475 TF. And then we're going to take 29.3475 times 45.8, and that gets us negative 1344.1155, and set that equal to, again, distribute. So we still got the negative out there, 440.154 minus, now take 440.154 times the 15.4, the negative 15.4, and that gives us, this is TF here, that gives us 6778.3716. Move my little box out of the way. And so then the last part is we're going to distribute the negative sign through the parentheses. So that will become negative here and positive here. And now our job is to get the TFs on one side and then the other numerical value on one side. So we would have 1344.1155 plus 6778.3716. And that gets us 8122.4871. And then we're going to add the 440 to both sides. So 440.154 plus 29.3475. And that gets us 469.5015 TF. The last step to solve for TF, we would divide both sides by that 469. So 8122.4871 divided by 469.5015. And that ends up getting us a value of 17.3 degrees Celsius as our final temperature. Okay, so it's all about the algebra and making sure you're putting things on the proper side. Remember, the hot object, whatever it loses, is equal but opposite to what the cold object gained. We're then plugging in the respective masses, specific heats, and then solving for that thermal equilibrium value, which would be equivalent on both sides. Final example, we have one final example here. So it says a hot piece of metal weighing 350 grams is heated to 100 degrees Celsius. It is then placed in a coffee cup calorimeter containing 160 grams of water at 22.4 degrees Celsius. The water warms and the metal cools until the final temperature is reached at 35.2 degrees Celsius. Here, we want to calculate the specific heat of the metal and identify the metal. Okay, because remember, specific heats are intensive properties, can be used for identification. So if we look at the information we know, we have information about the hot object, information about the cold object, and we're also told the final temperature. So in this case here, we're still going to use that Q hot is equal to, but opposite Q cold. But now what we're solving for in this case is the specific heat of the hot object, because that's the metal, and then using that for identification purposes. So again, we can expand out these this equation to say that it's equal to the mass of the hot object times specific heat times delta T, all for the hot object. is equal to, but opposite to, the mass of the cold object times the specific heat of the cold object times delta T. Remember, the delta T's on both sides are not the same. It's just simply the final temperature that's the same within that calculation, but the actual value is different. Okay, so now we can plug in. The mass of my hot object is 350. I don't know what the specific heat is. That's what we're solving for, so that remains the same. And then my change in hot temperature, I started at 100 degrees. And so we would put that in as our initial. And our final is 35.2. Okay, those are both degrees Celsius. So that's equal to, but opposite, the mass of the cold object, which in this case is the water, times the specific heat of water, which is 4.18 joules per gram per Celsius, times, in this case here, we would say that the final is, again, 35.2 minus 22.4, which is the initial temperature for the cold object. We then want to go ahead and do the algebra on both sides. So we could first start by doing 35.2 minus 100 degrees is the change in hot temperature. And we times that by 350. And that gives us on this side negative 22680 times the specific heat is equal to, now we'll do the same thing on the other side. So we'll do 35.2 minus 22.4 times 4.18 times 160. And that gets us negative 8560.64. Last step to get specific heat by itself, we're going to divide both sides by that 22. So that 8560 divided by negative 22680, and we end up with 0.377. Sorry, I wasn't tracking the units, but unit-wise, we do know that a specific heat should come out as joules per gram per Celsius. And if this is the value that I get, probably the item I would go about selecting, which is the nearest one, is copper. Perhaps it's a slightly impure material of copper, but based off of that, and this is the list of possible knowns, then I would go with that answer. I hope this information helped you understand how to calculate heat and how to actually calculate the amount of heat that's transferred between hot and cold objects. Make sure you guys comment, like, and subscribe, and let me know any other content you would like to see. Make sure you guys check back for future videos, and I'll see you in later ones. Have a great day. Bye-bye.